Hello everyone and welcome back to another episode on the series of complete reference to CUDA programming. So far we discussed about CUDA execution model. We understood what are the steps we have to follow in order to write any CUDA program. Now in this session we will start actually writing a parallel version of vector addition. So to do that, just quick recap. These are the steps we have to follow when we write any CUDA program. That is declaration of CPU variables, allocation of memory for the CPU variables, declare GPU variables, allocate memory for GPU variables. We initialize data in the CPU memory, copy data from CPU to GPU, perform parallel computation, and bring back results to CPU memory. Finally, we'll free all the memories. So these are the steps we'll follow while writing a CUDA program for vector addition. And we know that what is vector addition? It is simply we are going to declare arrays of size n, that those are a and b, let's say, and we'll perform corresponding elements addition of a and b, and that addition will be stored into the vector c. So this is simple for loop. Now our job is to parallelize this particular loop, so by creating multiple threads on GPU. For that, we already know how it executes sequentially in this fashion, and we have seen its parallel version by creating multiple threads. Now that we are already familiar with threads and block this organization, we will start with this case study of vector addition, and we'll follow exactly the same step that we have mentioned in case of your CUDA programming execution model. So first step is we are going to declare variables for CPU and GPU. And note that in case of CUDA programming, we refer CPU as host and GPU as device. And this will follow in upcoming all the programs also. So we are going to create 3 arrays on GPU side and 3 arrays on CPU side. To do that, we have to create 3 variables here. Those are of type integer pointer because we are going to store the integer values in those array, and the memory we are going to allocate dynamically. So that's the reason we are going to create first variables of pointer type, and their data type is going to be integer pointer. Now 3 variables we are going to create for CPU data and 3 variables we are going to create for the GPU data, because anyhow we are going to perform computations on GPU, so we must have some distinct notations for CPU variables and GPU variables here. And that's the reason I'm using convention here h underscore and d underscore before naming the variable names here. So h underscore stands for host side declaration and d underscore stands for device side declaration. As I mentioned, host is nothing but CPU and device is nothing but GPU. Now once we declare these CPU and GPU variables, we are now going to allocate memory for the CPU variables. And to do that, we will use malloc function in C to allocate memory dynamically. So here I'm using malloc function, and the number of n stands for number of elements, and every element of size integer, so that's why n into size of integer. This much amount of memory gets allocated, and which will be referred by using h underscore a. Same will follow for h underscore b and h underscore c. So these are the arrays memory allocation on CPU side. Once we allocate memory, we will initialize the data. Now to initialize the data, simply I'm using a for loop, and I'm just going to initialize array A and B to 2. So all elements will be initialized as 2. And the array C, all elements are initialized to 0. Then next thing is I have to allocate memory now on GPU side. So already I have declared variables D underscore A, D underscore B, D underscore C as GPU variables. Now I have to allocate memory on the GPU side. To do that, we are going to use a function that is provided in CUDA programming called as CUDA malloc, which just like your malloc function in C, which allocates memory in the CPU's memory. Similarly, we have a CUDA malloc function which helps us to allocate memory on the GPU. This CUDA malloc function accepts 2 arguments. One is the variable device variable, by which we are going to refer that memory, and other is size, that means amount of memory we are going to allocate. So here we have to allocate memory for 3 arrays A, B and C, and for that reason we will be calling 3 CUDA malloc functions. So first argument I'll passing here address of that variable D underscore A, and then the total size of memory that I'm interested in the allocation. Same we are going to follow for d underscore b variable and d underscore c. Note that now at this particular stage we are having 3 arrays declared on CPU side and memory allocated for those 3 arrays on CPU side. 3 arrays variables, those are declared on GPU side and memory is allocated for these 3 arrays on the GPU side. And CPU side we have initialized the data. Now next task is we want to perform this computation on GPU side. So obviously data must reside in the GPU's memory. As of now, we just allocated memory on the GPU side. Initialized data is still on the CPU side. So first thing we have to do is we need to transfer this data from CPU memory to GPU memory. Right? So to do that, we'll be using a function that is CUDA memcopy. This will help us to data transfer between host to device and device to host. That means CPU to GPU and GPU to CPU. And to follow the syntax like this. So first argument that we are going to pass is nothing but the destination address or the memory to which we have to copy data. Then next argument we have a source address, that means from which we have to copy. Then size of data, that means amount of data we want to transfer between host to device or device to host. And finally we are having something is called as a direction. Now here I can mention CUDA memcopy host to device. That means I want to copy memory from CPU to GPU. I can change this function if I want to copy data from GPU to CPU, like CUDA memcopy device to host. Right? So I'll transfer host array A to device array A, then host array B to device array B, and host array C to device array C. And again, in this particular computation, we don't need to transfer this array C to host array C to device array C, because anyhow it is initialized to 0. Rather than we can create array on GPU side and we simply initialize it to 0 on GPU side itself. But as we are copying, this is the first time we are referring this CUDA memcopy, so I transferred all the arrays from CPU to GPU now. Now at this point, whatever we have initialized in array A, B and C, now entire thing is copied to the GPU side. And now GPU is having data on which we can perform the computations. Now here, the next step is actual kernel launch on the device. That means actual GPU function we are going to launch. So far we have understood what is this GPU function, what is the significance of these parameters that we are passing, and now this here, earlier we had a blank function, that is function without taking any argument, but here now I am passing some arguments. Now here I am supposed to pass only the device arguments, right? Because in this function I will be accessing data that is present on the GPU side. So that's the reason I am passing here arguments as d underscore a, d underscore b and d underscore c. And the last argument is n, that is nothing but the size of arrays. Fine. So this is where we are going to launch a kernel or launch a CUDA function to be executed on GPU. Now question is how to decide how many threads and how many blocks to be launched here. That completely depends on what is your input size. For example, if I am having input size equal to, let's say, 128. Here input size is nothing but size of each input array. So if it is of size 128, then I can create one thread block and 128 threads. Right? So let's assume this is the simple configuration I'm having. Because I'm having 128 elements in my array, so I'll create one block and 128 threads per block. And now let's talk about the function definition. Here I'm using global keyword just to tell the compiler that this vector addition kernel function to be executed on GPU. Right? So note that by mistakenly I'm using here two different names here, vec add here while calling a function, and here I use vec add underscore kernel. Right? So that's my bad. But assume that both names are same. Now here I'm passing these accepting these parameters d underscore a, b and c. Now inside this particular function, if I'm mentioning this configuration while kernel launch, one block and 128 threads per block, immediately at this particular point I'll be having one block and 128 threads in that block. Now every thread is going to execute the below statements or statement mentioned inside this particular function. So every thread is going to execute first statement int tid equal to thread id x.x. Note that whatever we are going to declare inside this kernel is going to be the private copy of each thread. Now for every thread, this tid variable gets created, and for every thread they are going to call this variable thread id x.x, which is going to return its own id. So for thread 0, it will create tid variable and it will hold the value 0. For thread 1, it is going to create a new variable tid which is going to hold value 1. For thread 2, new variable tid created and which is going to hold value 2, and so on. So this will happen for 128 threads. Now all these 128 threads are having its own tid variable and its value is of its corresponding thread id value, right? And remaining next statement is it is actual performing addition of corresponding elements, right? So for thread 0, this tid variable will be 0, so it will perform c of 0 equal to a of 0 plus b of 0. That means thread 0 will perform addition on 0th element of a and b and will stored into 0th location in the array C. Similarly, if I take randomly, let's say thread id equal to 10, then the 10th or 11th thread is going to perform addition on 11th element of a and b, and which will be stored into the 11th location in the array C. And this is how all the threads can be executed in parallel. Note that we are having thousands of cores are available, out of which we created 128 threads. So all these 128 threads will be scheduled separately on 128 cores available in my GPU, and all these will be executed in parallel. Right? So this is how we can write a vector addition program. One thing you can observe here is the for loop is replaced with these parallel threads. Earlier in sequential version, if you recall, we had this particular for loop which is ranging from 0 to n. But now I created n number of threads and all threads are going to perform corresponding elements addition. And that's the reason this for loop is gone from this particular kernel definition. Fine. So this is how we can perform vector addition. But there is a problem. Oh, before that, let's visualize how it will get executed. In earlier case, we assume 128 threads per block, but it is not possible to depict in this particular slide. So that's the reason I'm considering the input size is n, and if I'm having one block and 8 threads per block, then this is how they are going to execute. So I'll be having block 0 in which the thread ID is from 0 to 7, and for every thread they are going to be having corresponding TID value, that is 0, 1, 2 until 7, and all threads will execute addition of corresponding elements here. Fine. Now there is a problem. If I'm having, let's say, input size is 32, then I can say one block and 32 threads per block. If the input size is equal to 64, I can say one block with 64 threads. Similarly, if input size we go on increasing and it is, let's say, suppose 1024, then I can say I'll be launching one block and 1024 threads. So if you follow this fashion, it is very easy to launch number of threads per block. If n is the size, I can say one block and n number of threads per block. But that is not possible because we have some limitation on how many maximum number of threads we can launch per block. So typically it is 1024 in the recent architectures. So that means the maximum block dimension is 1024. So I can launch at max 1024 threads in a block. That means we can launch maximum 1024s per block. So that means I can handle only if size is 1024. But question is, what if the size is more than 1024? Now I'm not allowed to launch more number of threads, more than 1024 threads per block, but I have data which is more than 1024 in size, and that is very common because we can expect in real-time computing, we'll be having that input size can be of million. But here in CUDA programming, I'm having restriction that at max I can have 1024 threads per block. Fine. So one solution to that is going to be using a stride, and other solution is launching multiple blocks. So in next episode, we'll try to explore how we can use this striding concept to handle if the number of elements are greater than what is the maximum permissible size here for block dimension.